Hello students, I Dr. Satish Chauhan welcome you in the video lecture series based on molecular orbital theory. In this video, we will learn molecular orbital energy level diagrams for heteronuclear diatomic molecules. Let us consider molecular orbital energy level diagram for heteronuclear diatomic molecule, that is HF molecule. Why these are called as the heteronuclear diatomic molecules? Because we are using two different atoms. In HF molecule we have H atom and F atom. So combination of these two atoms give rise to the formation of HF molecule. So therefore, as there are two atoms, therefore it is called as heteronuclear diatomic molecules. It is a heteronuclear diatomic molecule in which fluorine atom is much more electronegative than hydrogen atom. The electronic configuration of hydrogen is 1s1 and that of fluorine is 1s2, 2s2 and 2p5. The atomic orbital of electronegative element contribute more to the formation of bonding molecular orbital and less to the antibonding molecular orbital. Similarly, atomic orbital of less electronegative element contribute more to the formation of antibonding molecular orbital and less than bonding molecular orbital. That is, electron in the molecular orbital spend more time around one atom than the other. This causes charge separation, delta positive and delta negative on the atoms, and develops a dipole. Thus, covalent bond in HF molecule has highly ionic character. There is delta positive charge on hydrogen and delta negative charge on F, that is fluorine. While writing the electronic configuration of HF molecule, H atom, there are no electrons to be written as K shell. However, for F atom, for 1s2 electrons we write K, and for 2s2 and 2p6 we write L, because we know that in atomic structure or structure of atom there are K, L, M and N cells present in the atom. So if we consider the fluorine atom, the 1s2 electrons are present in K cell, that is first cell, and 2s and 2p electrons are present in the L cell. So therefore we can write the Kl for HF molecule. Let us consider molecular orbital energy level diagram for HF molecule. This is an energy axis. This is the 1s orbital of hydrogen. This is 2p orbital of fluorine. So p orbital contains three orbitals, 2px, 2py and 2pz. Here just one orbital is taken, that is 2px orbital is taken, because we have the configuration of fluorine is 1s2, 2s2 and 2p5. The two orbit 2py and 2pz does not take part in bonding. Just 2px orbital take part in bonding. Therefore, we have taken here 2p orbital. There is one electron in the 1s orbital of hydrogen. There is one electron in the 2px orbital of fluorine. The combination of 1s and 2p give rise to the formation of molecular orbital, that is called as sigma sp bonding molecular orbital, and sigma star sp antibonding molecular orbital. So we see that, so these are the bonding molecular orbitals and antibonding molecular orbitals. The one electron from hydrogen and one electron from chlorine gets filled in lower energy sigma sp bonding molecular orbital. We see that the energy gap, 1s orbital has higher energy but 2p orbital has lower energy. So therefore we've seen that electronegative atom is more contributing towards the bonding molecular formation of the bonding molecular orbitals, and therefore it has lower energy, so it is easily form the bonds with the other atoms, and therefore the energy is lower than hydrogen. The electronic configuration of HF molecular orbital can be written as Kl sigma sp2, as there are two electrons are present into the sigma sp bonding molecular orbital. Let us consider the bond energy and bond order in case of HF molecule. Energy involved in the formation of HF molecule can be calculated as number of electrons in BMO into minus beta plus number of electrons in antibonding molecular orbital, that is into plus beta, that is equal to 2 into minus beta plus 0 into beta, so that is equal to minus 2 beta. The bond order of the molecule is given by the formula. Bond order is equal to 1/2 number of electrons in BMO minus number of electrons in ABMO. So 1/2, that is equal to 1/2 into bracket 2 minus 0, that is bond order is equal to 1. The bond order is 1. The molecule is diamagnetic. The bonding molecular orbital is closer to 2px molecular orbital of chlorine atom, hence it has more character of 2px orbital. The antibonding molecular orbital is closer to 1s orbital of hydrogen atom, so it has more character of 1s orbital. HF molecule is polar in nature, and the HF bond is polar covalent bond. The bond length of HF molecule is 0.90 angstrom and bond energy is 135 kilocalories per mole. Let us consider the molecular orbital energy level diagram for another heteronuclear diatomic molecule, that is carbon monoxide molecule. Carbon monoxide molecule is formed by the combination of one carbon and one oxygen atom. Oxygen is more electronegative than carbon. The electron configuration of carbon is 1s2, 2s2, 2p2, and that of oxygen is 1s2, 2s2, 2p4. That means there are 4 electrons in the p orbital and 2 electrons are present in the p orbital of carbon atom. The inner 1s electron of carbon and oxygen does not take part in bonding, they remain as a non-bonding electrons. The carbon monoxide molecule is isoelectronic with nitrogen molecule with 10 electrons. Both have 10 electrons in their molecule formation. The molecular orbital energy level diagram of N2 molecule is similar to that of carbon monoxide molecule, except that energy level of oxygen are lower than that of the carbon atoms. Since oxygen is more electronegative than carbon, its energy level is lower than those of carbon. Oxygen orbital contribute more to the antibonding molecular orbital. The 8 electron in the bonding molecular orbital try to neutralize the greater nuclear charge on the oxygen core. Hence, polarity of carbon monoxide is low. Let us consider the molecular orbital energy level diagram for CO molecule. So these are 2s and 2p orbitals, atomic orbitals of carbon atom. These are 2s and 2p atomic orbitals of oxygen. The combination of 2s orbital will give rise to the molecular orbitals. These are bonding molecular orbital and anti-bonding molecular orbital. Bonding molecular orbital is sigma 2s and anti-bonding molecular orbital is sigma star 2s. Similarly, the 2p orbitals of carbon and oxygen combine with each other and give rise to the formation of bonding molecular orbitals, that is pi 2py and pi 2pz, which are having the equivalent energies. So therefore these are degenerate orbitals. Similarly, pi star 2py and pi star 2pz, these are having the equivalent energies and these are also degenerate orbitals. The 2px orbital from carbon and 2px orbital of oxygen combine together and give rise to the sigma 2px bonding and sigma star 2px anti-bonding molecular orbital. Let us consider the electrons in the carbon and oxygen. There are 2 electrons in the 2s orbital of carbon and 2 electrons in the p orbital of carbon. There are 2 electrons in the 2s orbital of oxygen and 4 electrons in the 2p orbital. The 2s electrons get entered into the bonding molecular orbital sigma 2s and into the anti-bonding sigma star 2s molecular orbital, as like this. Similarly, the electrons from carbon and oxygen enter into the pi 2py and pi 2pz molecular orbitals, and the 1 electron from and they also enter into the sigma 2px orbital. So this is the molecular orbital energy level diagram for carbon monoxide molecule. Let us calculate the bond energy and bond order for the formation of carbon monoxide molecule. The molecular orbital electron configuration of carbon monoxide molecule can be written as kk sigma 2s2 sigma star 2s2 pi 2py2 pi 2pz2 and sigma 2px2. The energy evolved in formation of carbon monoxide molecule is given as 8 into minus beta plus 2 into plus beta, that is equal to 6 beta. The bond order of this molecule is given as 1/2 into bracket 8 minus 2, that is equal to 3. Carbon monoxide contains triple bond and there is 1 sigma and 2 pi bonds. The bond length in carbon monoxide is 1.128 angstrom and bond energy is 2 to 5 kilocalories per mole. Let us consider the molecular orbital energy level diagram for third molecule, that is nitric oxide NO molecule. NO molecule is formed by the combination of one nitrogen and one oxygen atom. Oxygen is more electronegative than nitrogen. The electronic configuration of nitrogen is 1s2, 2s2 and 2p3, and that of oxygen is 1s2, 2s2 and 2p4. The 1s electrons of carbon and nitrogen do not take part in bonding. They remain as non-bonding electrons. The inner 1s electron of nitrogen and oxygen do not take part in bonding. The molecular orbital electronic configuration of NO molecule can be qualitatively obtained either by removing one electron from configuration of O2 molecule or by adding one electron to the configuration of N2 molecule. Since oxygen is more electronegative than carbon, its energy level is lower than that of the nitrogen. The oxygen orbital contribute more to the anti-bonding molecular orbital. The 8 electrons in the bonding molecular orbital try to neutralize the greater nuclear charge on oxygen core. Hence, polarity of NO is low. Let us consider molecular orbital energy level diagram for NO molecule. This is an energy axis. These are 2s and 2p orbitals of nitrogen. These are 2s and 2p orbitals of the oxygen. Combination of 2s orbitals give rise to the molecular orbitals sigma 2s and sigma star 2s. Combination of 2py and 2pz orbitals give rise to the pi 2py, pi 2pz bonding molecular orbitals, and pi star 2py, pi star 2pz anti-bonding molecular orbitals. Similarly, 2px and 2px of carbon and oxygen, nitrogen and oxygen combine to form sigma 2px bonding molecular orbital and sigma star 2px anti-bonding molecular orbital. As the energy gap between 2s and 2p orbital is less, they interact with each other. There are 2 electrons in the 2s orbital of nitrogen and 3 electrons in p orbital of nitrogen. There are 2 electrons in the 2s orbital of oxygen and 4 electrons in the 2p orbital of oxygen. The 2 electrons are filled in sigma 2s orbital, 2 are filled in sigma star 2s orbital, 2 are filled in sigma 2py and sigma 2pz orbitals, 2 are filled in sigma 2px, and the remaining 1 electron is filled in pi star 2py anti-bonding molecular orbital. The molecular orbital electronic configuration of nitrogen oxide molecule can be written as Kk sigma 2s2 sigma star 2s2 pi 2py2 pi 2pz2 sigma 2px2 and pi star 2py1. The energy evolved in the formation of NO molecule is 8 into minus beta plus 3 into plus beta, that is equal to 5 beta. The bond order is given by 1/2 into bracket 8 minus 3, that is equal to 2.5. The bond length in nitrogen molecule, NO molecule is 1.15 angstrom and bond energy is 162 kilocalories per mole, which is considerably less than that of oxygen and nitrogen molecule. There is one unpaired electron in the pi star 2py1 anti-bonding molecular orbital, so the molecule is paramagnetic in nature. Let us consider NO plus ion. The molecular orbital electronic configuration of NO plus ion is Kk sigma 2s2, sigma star 2s2, sigma 2px2, pi 2py2, pi 2pz2. Energy evolved in the formation of NO plus ion is 8 minus beta plus 2 minus beta, that is 6 beta. The bond order of the ion can be given by the formula 1/2 into bracket 8 minus 2, that is equal to 3. Thus, NO plus ion is stronger and shorter than that in NO. The NO plus forms stable compounds like NO plus HSO4 minus. The similarities between valence bond theory and molecular orbital theory. Both valence bond theory and molecular orbital theory explain the nature and formation of covalent bond in the molecule. Both valence bond theory and molecular orbital theory assumes that the bond is formed by only when atomic orbitals of the two atoms possess nearly same energy, appropriate symmetry about molecular axis, and good overlap with each other. Both valence bond theory and MOT consider that the concentration of electron density between the nuclei which develops attraction. Both valence bond theory and molecular orbital theory considers the directional character of covalent bond. Both valence bond theory and molecular orbital theory use above principle in filling the electrons in the atomic orbitals and molecular orbitals. Let us consider the difference between valence bond theory and molecular orbital theory. Valence bond theory, overlap of atomic orbitals takes place. In molecular orbital theory, overlapping and combination of atomic orbitals takes place. In valence bond theory, atoms retain their individual character when linked to the other atoms. In molecular orbital theory, atoms lose their individual character in the formation of bond and molecular orbitals are formed. Valence bond theory. According to the valence bond theory, atomic orbitals are monocentric and electron moves in the field of one nucleus only. According to the molecular orbital theory, molecular orbitals are polycentric and electron moves in the field of more than one nucleus. Electron pairs are localized between the two atoms. Electron pairs are localized over all the atoms. It is used for qualitative consideration. It is used for semi-quantitative and quantitative results. It gives simple pictorial representation of molecular structure. It has greater conceptual and mathematical simplicity. Thank you.